camera back on. Sweet. Okay, so this session today, the last one today, I'm looking at reproducibility and curation. And in the broader sense of the word, Prasad has offered to tell us about some of the work he's been doing and how important curation and reproducibility is for developing clinical workflows. Take it away, Prasad.
Thanks, Andre. Okay, so what we're doing with the clinical workflows that we're developing is trying to use physics-based modeling to help improve outcomes for patients. So we're trying to do this by developing automated image processing workflows, and we're doing this in a couple of different applications. One of them is breast cancer diagnosis and treatment, so trying to develop workflows to try and assist clinicians with these topics. And another one's also early diagnosis of heart failure. Now, as part of developing these workflows, we need to really demonstrate credibility in our modeling and sort of the results that we're generating. So we need to make sure that these, our workflows are replicable. They have good verification and validation, and there's also reproducibility in the outcomes. And this will ensure that it's quite critical that we try and achieve these to make sure that the people who are using this have good faith and evidence that our workflows actually do what we say they're doing. Okay, so I'm gonna, just to begin off with, I'm gonna go over very briefly sort of our breast cancer diagnosis and treatment workflow, just to give you an idea of what are the kind of steps that we perform, and it's quite similar across different types of workflows, but it sort of highlights some of the challenges some of the steps we're taking, and then I'll talk about some of the challenges relating to demonstrating credibility related to delivering these workflows. So breast cancer affects 1 in 9 women worldwide. Early detection can help the successful treatment of the disease. And there's different imaging modalities that are used for diagnosing breast cancer. There's X-ray mammography, where the breast is compressed between 2 plates. And there's MRI, where a patient lies face down in an MRI machine. And there's also ultrasound imaging, where the patient's lying on their back. And in each of these different imaging modalities, what a clinician's trying to really do is map information between the different images. And this strengthens diagnosis of the disease. So the real sort of test of diagnosis is, can you find the same feature across different imaging modalities that are providing slightly different information? Now, it's really difficult for clinicians to map this information between the different imaging modalities due to the large amount of deformation that each imaging procedure is applying. So this is quite a significant challenge, and limits how well, limits the success of both diagnosis and treatment procedures. So what we're trying to do is use physics-based models of the breast to simulate the deformation that occurs during each imaging procedure, and use these models to integrate the information from these images into one common sort of framework. So we can use these models to simulate mammography, embed the mammogram images into the models, then uncompress the models, and we bring the information from those mammograms, and embed them in that model. And we can do the same for the MRI and ultrasound, and we can use these models then to fuse the information. Now, once a tumor has been identified, clinicians also need to be able to predict where the tumors would move to during treatment procedures. And these treatment procedures, for example, surgery or radiotherapy, they typically can't be performed under image guidance. And the breast tissues are very soft. So as you go to a different position, it's very difficult for clinicians to try and pinpoint where those tumors move to. So we want to also use our models to help predict where the tumors would move to, and this will help improve treatment of breast cancer. So to try and address these challenges and help clinicians, we've been developing automated breast biomechanics workflows. And so the idea is we obtain images from the hospital, and then we perform some sort of data processing. So in this case, we would, for example, if we have an MRI, we can segment out the boundaries of interest from that MRI. And we use machine learning tools to be able to pull out the different boundaries of interest, such as the skin or the outer rib. So structures that are important for performing biomechanics simulations. And you can see a couple of other structures that we're trying to extract. So here, a key thing is that we're using machine learning techniques, and we'll come back to that and sort of highlight where data curation comes in, becomes very important for trying to develop machine learning models, and also in terms of how they are applied to new data sets. So once we have these segmentations, we can extract, we can convert the sort of boundaries we get into point clouds, and then we can fit anatomical models, which is the second step of the pipeline. So the idea here is that we've developed automated procedures that use statistical shape models to take the point clouds and get initial estimate well, effectively get these surfaces and fit, get these point clouds and fit mathematical surfaces to them. And this sort of, we can use information from the population to get an initial estimate of what that shape should look like. Then we can fine tune that fit to the data by using standard geometric fitting techniques. So this sort of approach we found is very automatic, it's robust, and it works when you have missing data or even noisy data. So once we have our anatomical model, we can now perform simulations. For instance, we can perform mammographic compression, and we can start to see, for example, how can we figure out where the tumor is in the compressed state from X-ray mammograms. Or we can simulate how the breast tissues change shape as a person goes from the prone position where they're lying face down to the supine position where surgery or radiotherapy is performed. Now, once we've done that, we want to make sure that we want to build tools that clinicians can use to interact and visualize the new information that these models are providing. And we want to be able to then take these tools and make them available in the clinic such that they can be used to help diagnose and treat breast cancer. So that's a bit of an overview of this workflow. And together with our clinical collaborators, we've implemented this workflow at Auckland City Hospital. And I'll give some details of that implementation shortly. But before that, here's a look at what the tool that we've implemented for our clinicians. So here's an example of an MRI, a diagnostic MRI, a slice of a diagnostic MRI image, and the associated model that we've automatically constructed from that. And on the right-hand side, so on the left-hand side, we're showing a diagnostic image that was captured while the patient's lying face down, as shown here in this imaging slide. And on the right here, we have a prediction from our biomechanics model of where the tissues have moved to when the patient is lying on their back. And so this represents new information that a clinician would not otherwise have because the supine MRI are not acquired in the clinic. So what a clinician can do is scroll through these images and click on any point they're interested in, and this tool will tell them where that point would move to, from the prone position to the supine position. So in this manner, we're providing information that a clinician would normally have to figure out in their head as to where the tumors would move to. Now, another thing we're also doing is trying to use mixed extend these workflows to start using mixed reality technologies. So the idea here is that not only do we want to be able to get MRI images in the clinic, we also want to use some of the new technologies that are available. For example, this mixed reality headset from Microsoft called the Microsoft HoloLens. So the idea here is that we can use the sensors on this device to look at a patient and automatically construct a model, and then use our biomechanics workflow to predict how the breast tissues move as that patient moves around or is controlled by the clinician. And then this headset also provides tools to be able to project the tumor locations, for instance, which have been generated by our workflow onto the field of view, this visor here on the system, and that'll effectively allow the clinician to see the tumor directly on the patient. So it's sort of, this is sort of where we're going to. Now I'll get into some of the details of, you know, how are we attempting to try and demonstrate credibility in these workflows that we're developing. And I'll start off with looking at replicability, and then we'll move on from there. So in terms of replicability, maybe what we can do is take you through some of the infrastructure that we've developed. So at the moment, we have a workflow that's triggered from the hospital that runs our workflow at ABI, so outside the hospital. So the idea is that we can obtain, we can get access to clinical recordings from within the hospital, and there's a step where we can perform de-identification of that data. That data gets securely transferred to ABI, and it triggers a workflow, our biomechanics workflow. Once we have our results, the data is de-identified upon when we send it back to the hospital, and then the results are available to our clinician who can access these interfaces within the hospital. So in order to make this replicable, one of the things we've been doing is developing container-based approaches for each step of this workflow. So here we're using Docker, but we're also moving towards Singularity for a little bit more security. We also have, you know, to get access to this data, what happens is that a research nurse, typically for research studies, a research nurse has to get consent from patients. Once consent has been you know, approved by the patient, then we need some sort of a portal that allows a research nurse to be able to, from within the hospital, send that data over to us. And we've developed these portals to allow us to achieve that. And this involves de-identification of their protected health data following some standards in terms of, in this case, HIPAA standards. Now, once that data comes to ABI, we store that in our packs, and we have developed also container-based approaches to you know, deploy pack servers as required. Now, once they come to ABI, we can trigger our workflows, and we have a process manager that's developed in Python that allows us to run the series of steps that we perform in our workflow across you know, many cases. Any case that comes in will trigger a new sort of set of steps. And one of the things that we really wanted to make sure we do here is that for each step of the workflow, there is parameters associated with that. For example, the segmentation or even the simulation step, each of them have parameters, and we want to be able to capture that metadata at each step and propagate that as we work through each step. So we know where, you know, where the parameters and the data came from. The other thing is also that we've created the documentation for all of these aspects. So the idea is that anyone who can read this documentation will be able to deploy a similar sort of a setup. And this work has really been driven by Chin Lin, who's our web developer in the breast group. So we have this workflow completed, and we can actually run it between the hospital and ABI. One of the things we're working on now is trying to get this workflow running entirely within the hospital. So the idea here is that we directly embed our clinical workflows on servers within the hospital. So this simplifies the consent and ethics requirements procedures and allows us to perform pilot studies or even clinical trials within the hospital. And we're working on this together with Anthony Doyle, our clinician, who's been helping us on this project. So the next step after that is to try and incorporate the results from our simulation back into electronic health records. It's a pilot study to demonstrate that we can provide value back to the sort of the clinical workflows. So now, and we've identified through our clinician, we've identified exactly what he wants from our workflows, so he can actually see in patient reports. Of course, this is all still in research, so before we can actually make use of that for real diagnosis and treatment, it needs to go through clinical trials and be approved, but this is more of a proof of concept to demonstrate that this approach can work. So that kind of gives you an idea of how we've sort of tried to make our workflows replicable and make sure that they're sort of can be deployed. And the idea here is that we've deployed this at Auckland City Hospital and ADHB. We have other clinical collaborators, such as a surgeon we're working with at Waikato Hospital, who wants to deploy these at his hospital as well. So we need to make sure that we can, the tools that we develop can be implemented independent of the infrastructure. Now, sure, there is specific infrastructure that for accessing the data, and we're working on trying to develop. First of all, we need to get it working for one hospital, and then we can start extending that across to multiple different hospitals. So the next step I'll talk about is on verification and validation. Now, and sort of highlight how we really need to, and actually the majority of the work in this field of clinical translation is really aimed at verification and validation to prove that the outcomes are as you would expect. And curating data is an important aspect of this, which I'll go into a little bit of detail. Now, I mentioned uncertainty quantification here. I won't go through that in this specific talk, but towards the end, you can ask any questions. We've been working with the engineering science department and developing methods to be able to allow us to really look at how uncertainties in our data propagate throughout our workflows, and how we can start sort of making understanding the results from our workflow from the point of view that there is uncertainty, and that will impact our ability to verify and validate these models, and also our ability to reproduce results if someone else were to try and run workflows using the descriptions that we provide. So okay, so I'll talk about this verification and validation. So a large part of the work that we'd be doing is making sure that the underlying methods that we are using in these workflows are verified and validated. So this part of this is to try and isolate the complexity of modeling the complexity of modeling the human body from actually making sure that the methods that we're using satisfy basic physics principles. So in this case, we've been using a lot of soft tissue phantoms. So the idea here is not to replicate the tissue function, it's to simplify the problem such that we can actually ensure that our methods are working as we expect. So for example, here, if we want to simulate gravity loading, which is one of the main things we're doing with the breast, we want to make sure that our models can actually replicate gravity loading of a simple cantilever beam. If it can't do that, then we have a big problem it'll never work on real data, on actually the breast itself, where there's even more complexities. So we're using these models to, these soft tissue phantoms, to try and really get our heads around how are we actually modeling, how can we model these different physics and make sure our models are doing what we expect. Now, as part of that, we've also had to develop a lot of instrumentation to be able to collect data from these phantoms, collect rich data that will allow us to verify and sort of validate, in this case, our modeling approaches. And some of these devices, we also aim to translate them and use them as part of, even in soft tissue studies. And some of them we've already have been doing that. But the first step, of course, is make sure things are working well on these soft tissue phantoms. Okay, so now we have some confidence that our underlying methods are accurate. What we need to then look at is checking that our workflows also work with real patients. And to do that, we need to get access to data. So one of the things that we've been doing is, one of the things we need to do to develop these workflows is get access to the data. And thanks to our clinical collaborator, Anthony Doyle, he's got us access to over 200 data from over 200 breast cancer patients. These include clinical prone MRI images. You can see some examples there. And this also came along with X-ray mammograms and ultrasounds from the same patient. And we store these in our packs securely in our packs at ABI. So this alone, this will really allow us to test our ability to construct models from these kind of images. But it doesn't give us any idea of whether the models are doing the right thing, because we only have a single image here. And it's the image that comes in. So how do we know that the outputs from our workflow, for example, the prediction of the tissues where they move is accurate? Well, we can't from those images, so we've had to collect our own data. So we've collected MRI images from over 114 healthy participants. And the idea here is that we try to make sure that we can get the best data we could. So we tried to make sure all the boundaries were visible and very high resolution, as high resolution as we could get. And we tried to get these in different positions so we can start trying to look at the accuracy of our models. And you can see the difference between these two sets of images. So our workflows need to be able to work for both of these types of data. And currently we're at least the model construction stage, we can actually handle both these types of images. So an important part, now we've got this data, we need to be able to look at managing this data and being able to access information from the data to make use of them in our clinical workflows. So just to give you an idea of what we do, or how we've been attacking this problem, is we store this data on our university's Center for E-Research on drives provided by our university Center for E-Research, and we're really grateful for that. And what we've done is we've sort of, as a group, we've defined the structure that we want to store this data in, and this includes the original data and also processed sort of analyses. Now, one of the things we need to do is keep information regarding the data with that data. So this is where metadata comes in. And we really wanted to make sure we were trying to use best practice, best standards. So we went over to talk to Andre and Tommy and Alan, and we got some really good advice on how we could start sort of storing our data in formats that address a lot of the issues a lot of the issues that we have when you're trying to interrogate that data set and use that subsequently in your workflows. So what we've done is we've sort of defined metadata schema that we can that describes what the data is, and that's stored in this turtle format. And then we use the shape constraint language for validating new entries, which are written in JSON LD format. And here's an example of that schema. So we've got some tools to existing tools that we're using so we can actually take new data and validate that and make sure that it conforms to the schema before we incorporate that into our databases. Now, one of the things that's quite prevalent in research, especially when you're dealing with students and researchers that are not very familiar with best practices or typically aren't trained well, is that what you typically find is that if you got data stored in some sort of directory structure, what people end up doing is hard coding paths to data and trying to go in there, and all their code for using this data is got paths all over there, so you can't actually take that and reuse it. You reuse their code without having to change a lot of code, which isn't exactly best practices. So one of the things we were trying to do is also move away from this and make sure that our students don't try and even ourselves, we don't try and fall into this trap. So one of the things that we've been doing is developing modules to allow us to be able to access the metadata or even add new metadata. And the idea here is to provide some way such that our modeling pipelines do not actually ever need to know, or the user doesn't ever need to know where the data is. The metadata provides all that information. So we've been implementing these. We've implemented a Python sort of module that allows us to access that data and use it, use that consistently throughout the different workflows that we're developing, and also for research studies that our students are performing. Now, this sounds like we're kind of, one of the things is that ourselves, we're not experts in this field, so we really kind of trying to get advice from the experts, and many of them are in the room at the moment. And including others, the communities that are actually really good at, have made major strides in defining tool standards for being able to work with metadata and use it. So from our point of view, there's a lot of challenges. So one of the things we're doing is that we're not using standard schemas. We've got this basic version control, which is quite scary in case something actually we need to change it. And it took us 3 months, for example, as a group effort to define what exactly do we want to have in those metadata. This was in the heart group, for instance. Now we are currently also storing these as files, the metadata. Should we be using a database? How do we maintain such a database? We've got 5 or 6 people in the group. Do we have the resources to be able to do that? We want to try and keep things as simple as possible. And then how do we go about even version controlling the data itself? So these are still questions, and we need to really get some advice from the community on how we can help solve that problem. So these are sort of ongoing challenges, and I assure you that these are challenges that everyone, all the groups, most groups at AVI would be facing similar challenges, and the tools that we have and the knowledge that we have is not as sort of advanced as the computational biology community, which is awesome. So it'll be really great if we can start building upon your knowledge to try and help solve some of these issues. Okay, so we have our data, and we have descriptions of that data. So with that, one of the things we want to do is make sure we can visualize and annotate that data. So we've done this by developing some tools in the backend that we can use our metadata modules to access information. And then we can use a front-end web server based on JavaScript and 3JS, which is really well documented, and and there's lots of resources on how to use that. So we can start visualizing all the data that we're using and also some of our simulation results. So in this manner, we've developed ways to be able to segment contours very quickly. We need efficient ways to generate annotations that we can use to develop workflows, train machine learning models to segment MRI images, these kind of things. So we've actually we've got now a consistent way to be able to construct segmentations, which I'll show you where we start using them. One of the things we're also doing, and this is really a work in progress initial, is to try and start annotating this this data such that it can be so it kind of conforms to the FAIR standards which you've heard about previously, and also trying to identify the sort of the terminology and the different aspects that we're working on. For example, if we're going to pull out skeletal landmarks, we want to make sure that we can annotate those correctly. So that's a real work in progress, and that we also need some guidance on. Okay, so we've been able to store our data and be able to visualize that data and pull out annotations. Now, one of the things that we need to really take care of doing is curating data. And here's an example of where this is quite important. So like I'm saying, it's essential for developing and applying these workflows. Let's take, for instance, the data processing step of our workflows. So that was that first step that takes the images and extracts the boundaries of the tissues. So it's a segmentation aspect. So we use machine learning to achieve that. And what is required for machine learning is that you need to be able to train that with something. So what we do is we take our original MRI data set. Ideally, we want to just hand this data set to our machine learning algorithm and it will automatically segment that. But to get to that stage, we need to actually provide it manual segmentations to train it. So I've shown you the tool that we can use to get these segmentations, and from that we can train these automated segmentation tools. Now, one of the problems with this is that these machine learning tools, they're typically only really valid when for a specific MRI sequence. For example, T1 or T2 weighted MRI is an example. So the training is really dependent on that, and we want to get the best accuracy. So we kind of trying to isolate to one of these sequences to develop models specifically for these sequences. Now, here's an example of a segmentation from an unseen patient where the MRI sequence matched the training data. Was similar to the training data that we used to train the machine learning model. And here's an example of what could happen if you actually don't use the correct sequence. So this seems like a problem we can avoid if we just know what sequence we're dealing with. Well, here's an example of the sequences that you get from a clinical scan of an individual. So there's a whole bunch of different sequences. There's non-standard labeling across operators, vendors, organizations. So this is a sort of very difficult to figure out exactly what, from this description itself, very difficult to determine whether this data is appropriate for our machine learning segmentation tool. So what we've done is we've actually developed ways to now access the MRI header, extract the sequence. We can access our packs automatically, access the MRI header, and extract the sequence metadata through our metadata function module. And the idea here is then we can start filtering this based on our MRI sequence parameters from the MRI sequence. So for example, echo time, repetition time, these are what define the type of sequence. So this allows us to have some measure of control on the quality of our data. And now I've explained this from the point of view of applying machine learning segmentation tools, but this same issues is there when we're training the data. So we need to make sure that when we train data, we know exactly what sequence we're dealing with, and we want to be able to make sure that we curate our data sets such that we can make very effective tools. If we accidentally had, like, for example, the T2 MRI in our training set, what that'll do is it'll reduce the ability of that machine learning algorithm to make segmentations. Ideally, we want to do that and try and apply lots of different sequences, but having targeted sequences also can help give you some good accuracy in these segmentations. Okay, so I've sort of shown how we can use where data curation is important, and how we've now got this access to this great data that we've curated. One of the things we need to do is assess. We want to start using this data to assess the accuracy of our modeling workflows. So what we've done is that together with our clinician, we needed to get some way of assessing accuracy of our model, right? So on the left here, we have our prone image, and on the bottom here, we have our supine image. So if we build a model from the prone, we want to be able to predict how the tissues move to that supine position. And we want to be able to check our model is correct or not. So together with our clinician, what we did was his team of analysts, registrars, they identified corresponding landmarks between the prone and the supine MRI images. And this provides us now some idea of where the tissue is moving, and we can start comparing our model predictions to these results. Now, one of the things with this sort of analysis is that it's very point-based and localized. So to address this issue, we've also been developing non-rigid image registration analyses that allow you to not only now look at individual points, but we can define fields of a map between the prone position and the supine position. This is very important to understand breast tissue motion, but also gives us some tools for assessing model accuracy. So we can start using these tools now to assess what happens as we add and remove components from our model. For example, on the left here is a model without skin, on the right is a model with skin. And we can start using these registration of the internal tissues and the landmarks to get an idea of whether the models are giving good accuracy or not. And we've repeated these kind of studies for a number of different, including and removing a number of components from the workflows. And in this way, we've kind of identified some of the important interactions, such as how the pectoral muscle can slide over the rib cage as you move your arm, and also the skin, which is quite important. So these tools, developing these tools, are quite important to allow us to continually sort of improve our models as our simulations, as we advance in ways of describing the breast tissue motion with our simulations. Now, that alone, just the data that I showed you there, prone and supine MRI, is insufficient actually for validating the models. So what we need to do is validation in the sense that we need independent data to be able to assess our model predictions. So to get this independent data, and in addition to our MRI, what we've been doing is developing new imaging systems to be able to image women in multiple positions. So in this case here, women can sit in this seat, and we can image them in the upright position, the supine position, the prone position. So here we're using some of the developments that I showed you earlier on that phantom slide, where we use instrumentation devices such as camera systems to be able to image the surface, the skin surface, and use that information for, we're trying to use that information to provide us additional data that we can use to validate the models. So the idea here is to put someone in these seats and hold their arms in different configurations, more than what is possible in MRI, so we can really validate our techniques, albeit only at the skin surface, but there's ways we can start addressing that with other imaging modalities, such as ultrasound imaging. So as I said, we can attach cameras to the frame and gather rich data for validating our mechanics predictions. And we're working with Breast Research Australia, where we can actually get this, they have a lot of experience with imaging women over a number of decades, and they have all the clinical and community links, both in New Zealand and Australia, to be able to image the breast. So we're really getting really want to get their assistance in gathering data using this tool so we can validate our workflows. Okay, so I've given you some idea of how we've, our workflows in terms of our implementation of the workflows and how we can try and get replicability and the techniques we've been using to verify and validate our models to really demonstrate credibility. Now, this last aspect here is reproducibility, which has been quite a challenge, at least to demonstrate that from our point of view for clinical workflow. So I'll give you some ideas of what some of the challenges are and sort of the next steps in being able to do this. So we know that reproducibility is an essential component of demonstrating credibility here, but it's quite difficult to do that for these clinical applications, especially for in sort of what we found, at least in our soft tissue biomechanics community. So workflows take years to develop and validate. So to sort of develop and validate our clinical workflow for prone to supine repositioning took 5 to 6 years. In terms of getting the data to sort of verify and validate these models, we need big data. Collecting this data is time consuming. It's actually valuable IP for commercialization. There's ethics and data privacy related issues. And there are some initiatives, for example, the Cancer Imaging Archive or the Cardiac Atlas Project, that try and provide mechanisms to allow people to share data, but validation data is typically not shared in this community for some of the reasons here. And that's actually quite a shame, because that actually, that's really important to try and, without that data, you cannot really reproduce these tools unless you spent as much time collecting that data to validate your modeling. So another thing is also we lack of tools and standards. So it would be really great if we had, for example, the CellML version for PDEs, so we can start encoding how we describe our model simulations and be able to exchange those in a way similar to how the computational modeling systems biology community has been working to great effect. So we're not alone in this sort of with these issues. So there's been some recent work in terms of trying to develop standards for these in silico models for personalized medicine, which try and build off the great work that the systems biology team have been developing. I think from our point of view, what we need is some guidance regarding what tools and standards to use and how to work towards trying to integrate them with the work that we're doing. And in terms of really trying to get an understanding of how can we actually contribute, because it's one thing having an idea of what we need, but another thing is the next steps that we need to take. And I mean, from our point of view, we can start by trying to provide the community challenges, simulation challenges that at least try and test different aspects of our workflows. And there's a number of these already available. For example, in the musculoskeletal community, modeling community, they have some of these challenges. And also, I haven't named any of them, but there's a few out there that we can start using to make sure that even though we might use different simulation techniques and software, that we're getting the same, that we can get the same outcomes. And one of the things we are also looking to do is start to release validation data, both on phantoms and volunteer data. And this is where being able to, make sure those models adhere to, for example, FAIR principles is quite important. In actual fact, one of the sort of initiatives we're developing is just like how the Cardiac Atlas project is providing data for individuals or researchers to be able to construct models and use data, clinical data of in cardiac imaging to help with their research. We would like to also do that for the breast, and we've actually got some funding from the New Zealand Breast Cancer Foundation to provide the Breast Atlas project, where we would be going and getting a permission from individuals to contribute their data to these repositories, so we can start making, having some sort of way to provide this this important data for ensuring we can others can reproduce the results that we generate. Okay, so just to summarize, we've been developing automated breast biomechanics workflows to help clinicians diagnose and treat breast cancer, and I've kind of outlined the need to demonstrate credibility and some of the challenges that we're facing. And one of the key things which I didn't mention also is that the need for training students and researchers, especially, we are quite sort of lucky that our institute, ABI at least, has very strong, they make a lot of contributions to this area, and there's a lot of experts in the field, so we have people to go to, but there's a lot of groups and a lot of groups around the world that may not have easy access to that sort of knowledge. So we need to sort of be able to provide that information. And a big part of this is training our students and ourselves on how to actually do this, at least in our community, as we are definitely not experts in software, and most of our time is spent validating and trying to verify and validate these workflows. So having some way of documenting, now I understand that there's a lot of there's some of these tools available exists for training individuals, especially in the reproducible science, the Center for Reproducible Modeling, which Andre was talking about. But it's and also the Combine and the hackathons that are performed there. But it'll be really nice to provide some sort of a beginner's guide for our students and researchers to be able to get into this field. So on that note, I'd like to thank our team here and our clinical collaborators who really helped us gather the data for these kind of studies, our funding sources to help us actually be able to do these studies, of course, our students and our collaborators, and also Martin and Paul, who've been great mentors in this on working on this project. So thanks about that. Sorry, I think I went quite over time, but hopefully this gives an idea of where we're sort of coming from in trying to make sure that our models are reproducible. Thanks, Andre.
Thank you, Prasad. Very good. Do we have any questions?
Prasad, can you hear me?
Yes, I can hear you, Peter.
I'm just wondering, something I was talking to Ellen Garney about this morning. Have you thought about workflow standards? In other words, if you've got a whole workflow process, can you define that whole process in terms of various, what one of the standards that have been developed for describing workflows?
I missed that last bit, but it sounded like, can we describe the steps that we're taking? I think we've documented what we're doing, and we've been trying to look out for different ways that people have been developing these workflows. For example, there's one called Chris from the Boston Children's Hospital, and they've been developing infrastructure very much like what we've been developing, but there's a whole bunch of software developers on that team that are developing quite complex, from our point of view, workflows that will allow you to, execute similar sort of analyses. Now, in what we're trying to do is make sure that we're working towards certain standards. For example, HIPAA, make sure that we're dealing with privacy well. We do need to see what else is out there so we can start sort of, as you said, taking advantage of some of the standards that are already available. At the moment, we've been focusing on just documenting our specific procedures and making sure that some of the standards are the standards that we know about are adhered to.
Yeah, maybe something we want to talk about in relation to 12 months.
Yeah, absolutely, yes, absolutely.
Fantastic talk, by the way. Thanks.
Thank you.
Questions? See if you're on Zoom. So if you're on Zoom and have a question, please shout it out. Prasad, I was just wondering, when you have done some validation or checking of any of these results, have you looked at all that's how you store or archive that knowledge?
So yes, that's been a challenge. I would squarely put that in the work in progress category. So actually we have so once we do these analyses, the idea is that they're supposed to be version controlled and separate. So how the workflow is being set up is that you can have different instances of the entire workflow. But actually we haven't got to the point yet that we have a stable enough sort of workflow that we would want to keep the results, you could say like that. So that's been continuously improving, and at this stage, we haven't actually applied it anywhere. So other than, for example, publishing. So yes, we've thought about how we could do that. In terms of implementing it here, I think we need some advice on how we could best do that. We've at least figured out where we want to put the data, and from the heart group, we have some ideas on how to actually follow that through and store it separately and use metadata to annotate that. That's really how we want to do that, is to use metadata to say, this is how, after we run the workflow and we get a propagation of all the metadata at the end of the workflow, we need to store that. And that's actually, at the moment, our only mechanism to do that. If you have some ideas on that, would be really great to hear them.
Sorry, not yet. Yeah, it's something to think about as well. Any other questions? So I think tomorrow we just talk on 12 to see how some of the starts to link in some of the other work going on around the place as well. Okay, so if there's no hidden comments on Zoom or somewhere, so thanks, Prasad. That's very good.
Thanks.
We'll see you at dinner.
Yep. See you.
See you video. Okay, so now something a little bit different, but continuing on the same topic about reproducibility and curation. What I would have liked to do is get a name to get this off. Unfortunately, he's on holiday. So I threw something together and we'll see how it goes. But essentially, this is trying to look back. So called it curation and practice. And it's really looking at this pilot we did with PLOS computational biology, where we were evaluating reproducibility. And some random numbers were pulled out of that. The very first lesson we've learned, and I learned late last night, is that when you're not sitting next to someone, we're not really documenting things well enough in terms of what we do for curation in these checks. Because without the man broke his eye to tell me exactly what he means by certain words and certain things, we've got information all over the place in terms of spreadsheets, Google Drives, and things. And we are definitely not doing a robust enough job tracking the curation. That's lesson number one. But essentially, in the Reproducibility Center, as I mentioned briefly this morning, we're looking at how we can work with journals to improve reproducibility. And really also, how do we develop common curation practices so that when different people curate a model or check a model for reproducibility or other types of checks, what do we mean? At the moment, we all mean very different things. And I think you just saw a good example from Prasad, where he's talking a lot about curation. And that's very different to what we mean when we curate a CellML model, for example. So then, are there sort of domain-specific practices versus general curation that can be common across all these areas? I think, you know, it's probably very important just to emphasize that when we talk about curation, we're not talking about validation. Yeah, I think Prasad did a nice job. We separate the sort of purification and validation from the actual curation. We just sort of curation, you're checking that what's written down essentially is correct. But you're not saying it's a good model, good data. And then really, how do you measure reproducibility? Various people have various ideas on how to do that. And we're trying to see how we can all coordinate together. And it's also important to note that once you start slapping metrics on something and saying this is good, this is bad, there's many pitfalls associated with that. So we'll be very careful, especially when you're talking about journals and publications, because that's what people's careers are based on. And annotation, we'll talk about already. So in terms of this curation service, this was the original idea. And as you can see, you know, this idea of essentially an author submitting a model, iterating with the curator sort of talking directly with the author to say, hey, this is wrong, how do I fix this? Then eventually, once it's all good, you submit it to a journal. The journal has the review, the normal scientific peer review, and they'll typically maybe look at the curation report or something as part of that, make a recommendation, and it all gets published and the model publicly available. That was the goal. That seems how we've been doing it for many years. But what actually happened with this pilot with PLOS is they very much wanted to keep the traditional submission pipeline, so we just could slot straight into it. So essentially, an author's submitting a manuscript to PLOS computational biology, goes through the normal process of associate editors, going to send out for review. And then what we tagged in as the extra bit is the author could opt in as an optional thing at present, or at least during the pilot, to say they were happy for their manuscript to be checked for reproducibility. And when they did that, if the associate editor deemed it a suitable manuscript for us to look at, it would get sent to us for a technical review. So while this is fitting in with the normal sort of review and the peer review process, we were only doing a technical review. We're just checking it for reproducibility. We weren't doing a normal scientific review. The editors taking part in this all knew this, and so they could interpret our reports as not being a scientific review. And essentially, it was a small extension, I think, to the editorial manager system that they use. They have a sort of technical review rather than a scientific review. At the end of that, we would submit a reproducibility report. It was a review of the manuscript that would go back to the associate editor for them to help make a decision on what would happen. In a very brief screenshot that you can't read, that's the reproducibility report. There's a basic summary at the start to say this was cool or this was bad, and a bunch of checks that were done, that were ticked and not ticked, and then a sort of summary statement at the end with a bit more detail on what was done and how well it worked. So just to show you in a bit more detail, as I said, first just a bit of very one sentence type summary of how it went. Then going through looking at things like, was any code provided? Is it in a standard procedural language like Math, C, or Python? Is there a declarative language like XML, CellML, similar things? And how much details is provided? Is enough information provided to tell someone how to use it? If there's no code, is there something executable without source? Maybe a desktop application or some online service. And again, is there enough documentation on how to use it to reproduce the results? Then looking at things like normal, is the math described in the article, other equations, parameters, initial conditions. We were starting to look at distinguishing between here's a list of parameters, and here's a list of parameters that you can actually load into a piece of software. As soon as you're typing in numbers from a paper, you can introduce errors. So if they make the numbers available in a way that can be read, it's better. And then are the simulations you need to perform described in the article? Things like the integration algorithms, the stochastic algorithms, random number generators, things like that. They need to be able to reproduce the result. Then we looked at accessibility. Basically, is the code available, preferably in a public repository on the web somewhere? And again, are all the initial conditions and parameters provided, and the simulation experiments fully defined? And then a final sort of summary. So this is an out-of-date version of the report, which you should have noticed before. But essentially, there's also been now introduced the critical practices for simulation. So they have 10 criteria, which we're also evaluating. So in this pilot with PLOS, we're sort of really looking at reproducibility and reproducibility of articles submitted during this particular period. And there's a few things that were published in PLOS telling people about it. And the pilot started at the end of May last year and ran for about 3 months. This is a set of questions we came up with the editors of PLOS Computational Biology that we were trying to answer. And really just to evaluate how, to have something to evaluate whether or not we're successful and whether or not people would want to do this. So things like how popular is the desire to publish reproducible models, and so on. And particularly, can we identify anything that your training should be given to help improve? So then just looking at how things went. So we ran from essentially May to August last year. There were 72 papers submitted to PLOS, where the authors indicated during this time that they wanted to have a reproducibility check. Did check the total number of papers submitted. Completely forgotten it, but it's somewhere a lot more than 72. And so of that 72, we've essentially done 56 of these technical reviews, including 10 from resubmissions where the papers have been revised and resubmitted since the pilot finished. And as you can see, of all of this, there were 18 that were reproducible, where essentially we could reproduce at least one figure on the manuscript. Then in general, a lot of the others you see, there's no code, missing data, or the usual code will be provided after data is accepted, missing files, documentation, so on, but we'll get into a bit more detail later. And so then working with WASP, we can start to see how things have gone in terms of the actual decision on whether or not they should be published. You can see some were transferred to other journals, some were rejected, and in some cases, but not all, as much as we hope, the reproducibility report was cited by the editor as part of the decision as to whether or not to reject. And of the 10 resubmissions we've seen, 4 of them that were not reproducible managed to address the problems that were identified and became reproducible in the resubmission of the manuscript. So it's still not putting enough effort into analysing the numbers we have, but a very quick analysis shows that essentially around 30% of the manuscripts we checked just had no code, so can't do anything. 15% had not sufficient documentation, so they didn't describe how to use either the code or executable or website they provided. 6% had runtime errors, so you run the code and it will just crash or not run. There were a couple that needed data, which either because of privacy reasons or health data, or just couldn't provide the data. There are a couple that just were not reproducible. Interesting. And also things like errors in compiling code or being unable to satisfy things like Python package dependencies when you try to install the code following the documentation. The thing that really worries me, and probably worries others, is that of the 11 papers that are not reproducible were still accepted by the editors, which is interesting. And obviously we're not doing scientific review, so maybe this is like groundbreaking work of some kind, but they're clearly not reproducible. So maybe just to emphasize, the reviewers of these papers are not seeking the reproducibility reports, it's only the editors. And it's not clear yet in terms of the final decision on it, publication or not, but these are people where it's essentially either accepted or, if you review things, this will be accepted. Otherwise, so I don't like the number. It's good. And it also, I think, highlights the fact that in general, when people review, they're not checking reproducibility. So that's a pilot where we had one person at the ABI, essentially an ANT, who for 3 months did this non-stop. It took a lot of work, a lot of effort for each manuscript that came in. And so that was 72 papers where the authors had, for whatever reason, opted in to have their work checked and be presumably thinking it would be reproducible. So what happens if we want to do that for all papers or more than one journal? It's interesting. I really have no idea what's coming on this slide. So in terms of journals, these are the ones we've been working with. So obviously Physio, which we'll talk a bit about tomorrow. There's another one that's already up and running as part of this. It's slightly different in that we have other curators in Auckland helping, and basically everything in Physio is reproducible, so it's easy to check. But then working with other journals like Cell Systems, the Biophysical Journal, and others, how do you resource trying to do this kind of checking, which clearly reviewers are not doing, how can we address these if we want to try and help all these journals. Obviously, this is still a very small focused subset of journals. So for the POS pilot, as I said, basically had a NAN going full time on this. And quite a bit of my time helping as well. Physio, we fit in directly with the curation workflow for physio. So it's a much lighter load, but still requires resource. And 3 more curators starting at ABI early 2021. Turned out not so early, and so far we have 2. We just started. So we're getting there. And as I said, if we want more journals, and then if we actually want to look at how we annotate the models as well as checking things like reproducibility, it's even more evident. I think the annotation is exactly where things like the Biomechanics data come in and getting that into tools. Essentially, what we need is lots of people, lots and lots of people. And they don't need to be experts, but they need to be trained in how to check these things consistently. So we know the editorial manager platform that computational biology and many other journals use can handle this and can do this sort of technical review. And the POS pilot shows that it worked, it was working well. And so how do we get a population of people who can do these technical reviews and then encourage them to do so? So the idea we're currently working towards is, can we train graduate students, particularly in the US, to do this kind of curation? How do we entice them to do it, besides supervisors telling their students if you don't do it, fail, which apparently is a bad thing, you're not supposed to do it. So how can we train them to do this consistently in their own particular domain, so that when editors see a paper, they can flag the domain it's in and go to the right sort of reviewers. And then part of that training, if we can encourage students to want to do this, and we can train them in how to do this, that will hopefully then also encourage them to adopt these kind of best practices in their own work, because they'll see this is going to have an impact in terms of their own publications. That's the idea, and that's what we're going to try and work towards. I think that's pretty much it. So yeah, so stay tuned. We're going to try and see how we can do this, work out how to train them, and how it fits into various efforts, particularly with the centre and some of our outreach activities that we're funded to do, and working with journals that are very excited to do this. Particularly POS, because they're already invested, keen and eager to do this across their portfolio. And if you've seen that they're starting to now make code itself required for submissions. So hopefully it's a short step from that to say the code actually has to work. That's pretty much it.
Can you explain what the minimum manuscript also reproducible?
They would have, yes. I mean, I don't know if they would have said, it's not reproducible or anything. But we do have that information and we're going through it now to pull out if there's any consistency. Part of it, I think, is because we are not iterating with the authors directly. So if there's trivial things that just stop you being able to run the code. Cool.
Would there be part of reproducibility stage to interact with the authors?
No. So in this system, we're not interacting with the authors at all. It's part of the review process. So with the the decision from the editor going back to the author would include the reproducibility report. So that would be the first the author would see.
Is it an issue between the editor and the sub-editors or the associate editors? Who's signed on to the whole process?
So this is all the associate editors are the ones who handle the review and make the decisions.
So they're the ones who sign this. That's the obvious question. Is it one?
No, so we ended up having interactions with many, much more than ever. So originally they expected to have 3, maybe 4 associate editors as part of the pilot. This is a much higher than expected response. They ended up with probably 8 or 9, I think, associate editors that we were working with from a very wide range of plans. So yeah, I think that might be part of it. This is some of the big models that are just not reproducible because they need things like some health records and things like that that they can't provide. Still, there's others with that sort of situation that provide the test data and stuff that they use to validate. It's not.
What do you state long term? I mean, you are saying, for lots of people, I can easily see that. But clearly, it is also in the interest of the journal to kind of find a way to contribute to it, right? Or is it just something that academics are going to be willing to do?
So at the moment, they're definitely looking at how can we do this without getting people to go to a different journal and not pay us money, and how to build minimal change to their existing processes.
But sure, we try to do that first.
That's where we're at. And I think part of it, working with some of the newer journals like Function, with AJP, they're partnering with Physio to get a better approach. Hopefully that's the more sort of long-term thing until such time as it's default. Everyone just puts models in PMR, everyone's reproducible, everyone uses the standard. Better long way. Any other questions, comments? Anyone with burning need to give a light to talk? Okay, so that's pretty much us for today. Final reminder, the most important meal of the day. Hang around at the ferry if you can. Same time tomorrow. Everyone was good today except one person. So hopefully tomorrow will be just as good. But yeah, otherwise the bus will be leaving at 10 to 4 past. A few minutes, everyone's finished checking emails. Thanks to everyone online for joining us. We'll try tomorrow to have a slightly better microphone, but no guarantee it's going to be a huge improvement. But at least it's much better now hearing people online. So that's good. Yeah, thanks.